we present our work titled Robust Long-Term Test Time Adaptation for 3D Human Pose Estimation Through Motion Discretization. Given input videos or images featuring a human subject, 3D human pose estimation aims to predict the 3D coordinates of the subject's body joints. This task is fundamental for understanding human activities and behaviors, where accurate body pose estimations could facilitate applications such as physical training, immersive interactions, and human-robot interaction. In the recent decade, learning-based methods have significantly advanced the generalizability of human pose estimation by leveraging extensive training data. Still, pre-trained models often experience a substantial performance drop when applied to test domains that deviate from the training domain. To address the inevitable domain gap, test time adaptation has been proposed. During the test stage, given input videos or images, these methods first update the model using self-supervised learning before doing the final 3D pose estimation. The adaptation process leverages supervision signals such as 2D joint detections or temporal consistency in human motion, thus capturing test time data patterns without requiring access to 3D ground truth. In this way, test time adaptation effectively mitigates the domain gap for enhanced performance. Nonetheless, we observe two main drawbacks in existing test time adaptation methods. First, these methods tend to be sensitive to self-supervised signals derived from imperfect 2D pose detections and 3D pose estimations. This sensitivity leads to error accumulation as prediction errors compound over time, thus hindering accurate long-term adaptation. Second, individuals often present consistent shape and habitual motion traits among action repetitions. When continuously observing and adapting to a single subject, model adaptation should benefit from capturing these unique personal patterns for more accurate estimation. However, the struggle with error accumulation positions continuous adaptation as also a risk, leaving personalized adaptation not thoroughly explored. In this work, we propose to address human body pose estimation from the perspective of online test time personalized adaptation. The test domain consists of streaming videos of the same person who was not included in the training phase. During test time, when each new video clip arrives, we continuously update the model parameters to perform on-the-fly adaptation and estimation for each video clip, which allows the model to capture personal traits throughout continuous observation. We further propose a new solution to mitigate error accumulation during long-term adaptation, which highlights using motion discretization and integrates an efficient yet effective soft reset mechanism to alleviate error accumulation. In this way, we enable enhanced performance through continuous personalized adaptation. We then describe the detailed implementation during pre-training and test time. We learn two components during pre-training. The first is a pose estimator that learns to output the 3D body pose from an input image. The second is an autoencoder-based motion denoising network. We further perform unsupervised clustering in its motion latent space, therefore constructing a codebook that contains representative codes in the latent space. During the test stage, given an incoming video clip, these two components are updated alternately. The motion denoising network takes the outputs of the pose estimator as input and leverages dynamics of human movements to refine the estimation. The outputs of the motion denoising network further serve as supervision signals to regularize the adaptation of the pose estimator. We leverage motion discretization to facilitate the adaptation of pose estimator. Specifically, when feeding the estimations into the motion denoising network, we exploit the latent regularity in measuring motion similarity to retrieve the nearest code from the codebook. This code is then decoded to obtain an anchor motion. We then supervise the adaptation of pose estimator using this anchor motion, as well as the output decoded from the encoded latent feature Z and the 2D joint detections obtained by off-the-shelf models such as OpenPose. We observe that this anchor motion could capture the core motion pattern of the observation. Meanwhile, discretization filters out high-frequency noise, making the anchor motion more robust against error accumulation and better preserving the motion regularity. Consequently, it enhances long-term adaptation. In the adaptation of the motion denoising network, motion discretization also benefits. Specifically, we randomly sample from the pre-trained codebook to generate a batch of replay motions. During adaptation, we combine these replay motions with test time estimations and feed them into the motion denoising network. We then supervise the adaptation using their reconstruction loss. With this kind of self-replay, we could retain pre-trained regularity without using pre-training images or motions. In this way, we enable generating consistent and regular anchor motion throughout long-term adaptation. Moreover, after adapting to each video clip, we perform a soft reset for the pose estimator by reverting its weights to its exponential moving average. This helps reduce the impact of noisy updates on individual batches, while keeping critical traits that are learned from historical adaptation. For experiments, we follow existing test time adaptation methods to pre-train the model on human 3.6M dataset, which is recorded in an indoor environment. We then evaluate on Ego XO4D and 3D-PW datasets, which represent in-the-wild scenarios. Specifically, for Ego XO4D, we evaluate on basketball, soccer, and dance scenarios, and use exocentric videos. For quantitative analysis, we measure the distance between the estimated joint positions and their ground truth counterparts. By comparing with the pre-trained pose estimator, we demonstrate that personalized adaptation alleviates the domain gap, leading to improved accuracy. Furthermore, our solution shows superior performance compared to existing online test time adaptation methods. This is attributed to our efforts in mitigating error accumulation. Qualitative results show that our solution enables more accurate and natural outputs throughout long-term adaptation. And we show comparison on another case from the 3D-PW dataset. We also conduct an empirical comparison with domain generalization methods that directly apply the pre-trained model to the test domain. These reported baselines are pre-trained on extensive datasets beyond human 3.6M. Our solution achieves competitive accuracy, further demonstrating our effectiveness in bridging the train-test domain gap. We further examine the benefits of motion discretization in long-term adaptation by plotting the error versus adaptation progress over time. We plot the error difference relative to the baseline that always starts from pre-trained weights for each incoming video clip, and compare our solution against a variant that removes motion discretization during adaptation. The results demonstrate the advantages of motion discretization in long-term adaptation and the performance gains enabled through continuous, personalized adaptation. In summary, we study online test time adaptation in 3D human pose estimation by focusing on a personalized test domain. To address the inherent challenge of error accumulation in long-term, self-supervised adaptation, we propose a novel solution that highlights using motion discretization and integrates a soft reset mechanism. By mitigating error accumulation, our solution enables performance gains through continuous personalized adaptation.